So let's look at kind of the origin on how and why we're getting to our atomic orbitals. So it's really coming back to our wave nature of light. Okay? So the textbook talks about some aspects of it. I'm not super concerned with it. In a full chemistry course, you would be expected to run a bunch of calculations, look at frequencies, wavelengths, energies, and all that fun stuff. For this class, you don't have to do any of those calculations. You just kind of need to know that they exist. That's really all I want you to get out of it. Okay? So light moves as a wave. Within that wave, we have a wavelength, which is the distance between peaks. And then we also have the frequency. So for a given interval, how many times does a peak pass? Okay? So if we looked at the wavelength of these two waves, the red one has a longer wavelength because the peak-to-peak distance is larger than the peak-to-peak distance for the blue one. Right? The frequency for the blue one is higher because if we pick an arbitrary distance, so let's pick purple to, let's go here, purple. How many times do we see a peak appear in the red one?
Once.
Once, twice, depending on how you want to count it. Let's just say once, that's fine. How many times do we see it in the blue one?
3 times.
3, 4, 5 times, more times. Okay? So there is a higher frequency in the case of the blue one, a lower frequency in the case of the red one. Okay? Notice that they are inversely related. Okay? The higher frequency has a shorter wavelength. The longer wavelength has a shorter frequency. Okay?
When we talk about this, are we talking about like light bulbs? Are we just talking like natural light or?
All light. Anything that you see is light.
Right.
Okay? Anything you don't see, believe it or not, probably also light. Okay? It's just a question of which light are we looking at. Are we looking at visible light or are we looking at some other form?
Okay.
Okay? So this applies to any technically part of the electromagnetic spectrum or radiation, electromagnetic radiation. Visible light is radiation. It just happens to be a very narrow section of it, which gets us to our next slide. And we're looking at our radiation waves, so things that generate or have energy and move in the form of waves. We can start all the way up at one end at cosmic rays, which really suck to get impacted by. Thank you, planet Earth. Gamma rays, again, thank you, planet Earth. X-rays, we actually use. But we don't want to be exposed to that all the time, right? X-ray techs typically hide behind big plastic, or not plastic, big lead shields, okay? And they hide back there while they fire these nasty things at you. Why?
Because they're really nice. And I can't figure out what's wrong with you.
Okay, we'll go with that. The X-rays are being used to figure out what's wrong with you, because those X-rays will pass through most of your tissue, but be stopped by bones. So we can get an image of your bones based off of that. Okay? Why do the X-ray techs have to hide behind lead shields? The X-rays are dangerous. So why are they firing X-rays at you if they're dangerous?
They're less dangerous if you're already dying.
Cost-benefit analysis. If you have a broken bone, are you willing to accept the fact of a little bit of danger with the X-rays if they can fix your broken bone?
Yes.
Probably. Okay? The X-ray techs don't have a broken bone. They don't need that little bit of danger. So they will hide behind shields to protect themselves from those X-rays. Right? As we shift further along, we run into ultraviolet light, followed by visible light, that tiny, tiny little line there that then we expanded out to all those colors. Infrared, microwave, TV, and radio. Right? The highest energy one are our cosmic rays. Super high energy, super dangerous. We don't want to get impacted by those. That's like not happy. Right? Radio waves, very low energy. Right? How might we guess that radio waves are relatively low energy?
We use radios every day.
We use radios every day. How do we get that radio signal? There's waves being passed out into the air that are then passing and moving around us. If they were dangerous, our lives might be a little bit shorter. Okay? So we want to kind of balance what we have access to and use some of that information because it can contain information that allows us to understand or transfer information. Okay? When we're thinking about the visible light spectrum, it is a very tiny section within it that transitions between all of our colors that we would expect within the rainbow. Purple all the way up to red, okay? Or violet up to red. What colors are in the rainbow?
All of them?
All of them. Okay, so that's an interesting observation. So if I asked you what colors were in the spectrum, what would you tell me? Okay, I heard someone shouting it out. Let's go with it. Turquoise will come back to. I heard someone say red. I heard yellow. I heard orange, green,
Indigo and
blue, indigo, and violet. Okay. Which, I actually kind of like that one better. That looks like Vib Igor. But it's usually spun the other way around. And as a memorization tool, we remember the name Roy G. Biv. And we now have the colors of our rainbow. And we've got them memorized for what goes into it. Right? Someone said turquoise. Where's turquoise in Roy G. Biv? Oh, it's a legitimate question. Why are we not listing turquoise as Roy G. Biv? It's a variation off of that, but orange, isn't orange a variation of red and yellow?
It'd take forever to list all the different colors.
It would take forever to list all of the colors. Okay? So what we've gone through and done is created arbitrary lines within it, saying that everything to that side is red, everything between there is orange, everything between there is yellow. Okay? We have arbitrarily put those lines on it and kind of just accepted those. Those are a human invention. Those are human lines. All colors are in that spectrum. Okay? Which, for those of you that may have watched the physical and chemical video for lab, physical and chemical properties or physical and chemical changes are a full spectrum. Okay? It's not physical or chemical. We have a transition between them that can be gray areas in between, just like with our rainbow. Okay? What other information do we want to try and pull out of this? Okay. We tend to see questions about energy. Okay. We could also see questions about wavelength. Energy is more fun, so let's stick with that. Which is higher energy, red or violet? Okay, violet. How do you know violet is higher in energy? Okay. So my answer would be, well, if we look at the diagram, it says energy decreases. So violet is over here, so red must be lower than violet. All right? Well, that was kind of a cheaty thing to do. I'm just reading the picture off because more than likely on an exam, you don't have that. So how can we remember that red is lower in energy than violet? Okay? We could look at wavelengths. How many of you want to memorize your wavelengths? So we're just saying red is lower in energy than violet. So instead of just memorizing that, I'm now going to memorize that the wavelength is different, which then tells me that the energy is different. Right? It's fine. You may very well have done that. Okay, we could try Roy G. Biv backwards. Okay. What's just outside of visible? Don't tell me invisible. Ultraviolet on one direction and infrared on the other. We walk outside during the summer in Arizona. What are we concerned about?
Sunburn.
The heat, sunburn. The sunburn's coming from what? From what? UV rays, UVA, UVB, UVC, UVS. Okay. We're looking at UV rays. What are UV? Ultraviolet. How many times you walk outside, you're like, oh, I got to cover up with my sunblock so that I don't get that IR. Infrared. Got to watch out for that. Nobody's concerned about the infrared. Okay, why? It's not harmful. Why is it not harmful?
It's not energy. It's low energy.
Low energy. Ultraviolet we protect ourselves from because it's high energy. Which color is closer to ultraviolet? Violet or red? Violet. You now have your tie back. Okay? Your violet color is your higher in energy, your red is your lower in energy. Okay? That's the way I remember it, at least.
Is that the way you remember it because you would think it would be opposite?
I try to avoid thinking outright. So, not quite yes with that statement. But I tend to get things backwards when it comes to memorization. So I need to come up with some kind of other world experience to tie it back to so that it triggers and it sticks for at least longer than a couple seconds.
Okay.
So that's usually where it comes from with me.
Cool.
Okay? So that's our spectrum. And so when we look at, say, white light, we take a bright white light and we shine it at a prism. The prism deflects all that light and we would see this entire spectrum, right? Anybody seen that before? Maybe. Okay. I wish I had a video. I don't. Sorry. Okay. But it makes pretty colors. We get the whole spectrum. Okay. So why is that then relevant to us? Well, someone went through and instead of taking just a white light, okay, because to generate that light, we take a light bulb with a little filament in it. We pump a bunch of electricity into it, and it spits out that light. Okay. And that bulb is in a vacuum. There's no other gases there. So somebody got the brilliant idea of taking that same bulb, except instead of removing all of the gas, they left some gas in there. But the gas they left in there was unique, okay? As in it was only one element. Okay? In this case, they put in only hydrogen. So what happened when we then pumped the electric current in? Well, the same thing happens. We get light. We get the conversion of electric energy into light energy. Except in this case, that light energy is coming from our hydrogen atom. And instead of seeing this bright white light, what we ended up getting was a neat color. Okay? Someone then said, well, that's a cool color. I wonder what it looks like if I pass that light through a prism. Okay? So if it's a purple color, we might expect a big purple spread of colors. Okay? And instead what they saw when they passed it through a prism was 3 lines. Not a big broad band of color, but 3 distinct lines. One that was red, one that was blue-green, and one that was violet. I said, well, why is that? What is going on? Why would I see those distinct lines? Something weird must be happening there. And so this goes back to understanding what we're doing when we're pumping the electricity in. Okay, what is electricity generating? I think we've talked about it in this class. Let's avoid heat. Electron transfer. It's electrons. So if I pump a bunch of electric energy into a sample of hydrogen gas, what is most likely moving in the hydrogen? The electrons. So somehow when I excite hydrogen gas, electrons do something. Okay? They're going to jump to a higher energy state. Okay? Most people jump when you put 15,000 volts in them. Okay? But once they're at that higher energy state, they relax back down. Well, that energy can't just disappear. It has to be released somehow. And that energy is getting released as light. Okay? Well, any model of the atom would show that. Okay? But if we used, say, Thomson's model, or a blend of Thomson's and Rutherford's, the electrons exist anywhere. Well, if the electron jumps from really close to the nucleus to really far away, would we expect that to be a big jump or a little jump? Big jump. Okay? We're virtually neutralizing the negative charge next to the nucleus versus not neutralizing it at all. So that's a big energy jump. When it comes back down, it would release an equivalent energy, okay, or an equivalent form of light representing that energy. If the electrons can exist wherever, what would we expect in our line spectrum or in our spectrum? Color everywhere, because the electrons can exist anywhere. We don't see that. What does that mean?
Atomic fingerprint.
Comes back to the atomic fingerprint, yes. The electrons can't exist everywhere. The electrons must exist in defined sections and only in those sections. They can jump from one section to another, but they cannot exist in between those sections. We have steps. Those steps are what give us the line spectrum. Without those steps, we see spectra, or a continuous color blend. Okay? Much like we saw with our rainbow. Okay? Yes?
You said that they can only exist in certain spectrums, but jump from one spectrum to the other. Does that mean eventually they pass through that middle spectrum? Or?
So they will have to pass through it, yes, but they can't stop there. So that would be like if we were on, well, let's see, do I have a picture there? Picture's here. So if I have that ball up on the top step, what are possible transitions that that ball can do? Okay, so we call that step 0. It could hop down. Can it hop down to step 1?
Yeah.
Yes.
Yeah. Could it hop down to step 2?
Yes.
How about 3?
Maybe.
How about 4? 5. All of those are valid steps. Can it hop down to step 0.5?
No.
The ball can't exist in that free space. It must be contacting one of those surfaces. So when we're looking at our energy levels or our atomic lines, we're representing steps. Our electron can only exist at a step. It can pass through that empty space, but it can't exist there. Can't stay there. What if we'd had a continuous spectrum? Well, that's like a ramp. That ball can exist at any and every point along that ramp, okay, or along that height. But our ball on the steps can only exist at those steps. Okay? So what we're looking at is something known as continuous or discrete. Okay? The ramp is continuous. We can be at any point along that ramp. The discrete means I can only be at individual steps. Okay? And we're not saying anything about jumping from step 0 to step 5. Because we can do that. Okay? I can jump all the way down. Okay? Maybe break my nose. But I can make that jump. Okay? The ramp, I would just roll down. Okay? But the steps, I can only exist at those steps. Okay? What does that mean back to science? Well, this is where we encounter the Bohr model. Niels Bohr looked at this and said, well, if that's the case, then that means the electrons can only be at certain steps. And so he started to define those steps. Okay? And this is an unfortunate feature of that screen, okay, versus this screen. So I'll try and draw over the top. And so what he drew was a nucleus in the center, and then said we had different steps. Okay? Fun thing about steps as a word is that used outside of science. Yes, which then means not cool enough. So what do?
Make it more cool.
We make it more cool by inventing a new word. What's our new word? An orbital. Okay. We could refer to it as an orbit, but it's not a really good term. Orbital is better. Okay. So what we're saying is the electron can only exist at those distinct levels. It cannot exist anywhere in between. So that if I say take my electron, more than likely it would start closest to the nucleus. Why would it start closest to the nucleus?
Because
That's where the electrons will hang out.
Why do the electrons want to hang out there?
This is cool.
because protons aren't they attracted to each other?
We're trying to neutralize charge. Where's our electron going to get? As close to the place where it can be neutralized. Well, if it's negative, what does it need to get next to? Positive, which is protons in the nucleus. So it will get as close as possible to the nucleus to neutralize that charge. Okay? If it does somehow scatter all the way into it, then it explodes, big violence. I don't think it explodes, but it doesn't work. Okay? We lose our atom. Okay? Now what happens if we come along with our 15,000 volt cattle prod? What happens to the electron? It gets excited. What happens when you get excited?
Jump around.
You jump. So what does our electron do?
Bounces around.
It jumps. If it moves up to that next energy, it is now at a high energy state. Okay? You're excited. Okay? Let's think of the last time you were all excited. Day 1 of class. Okay? How many of you are still excited? Okay? What happened? What happened to that excitement?
Words.
Words happened to that excitement. Okay? That excitement dwindled and slowly dropped back down until we reached the ground state that we started at. So our electron has been jumped, but now what has to happen eventually? It needs to come back down. The reason it jumped is because we gave it a cattle prod of energy. Well, if it comes back down, what does it have to do? It has to lose that cattle prod of energy. Okay? So in its process of coming back down, that energy must be emitted. Okay? I have to lose that energy. That energy happens to be in the form of the electromagnetic spectrum. For particular elements, it's not just part of the electromagnetic spectrum, it is part of one very important section of it. It is part of
Valence electrons.
nope. It's part of the electromagnetic spectrum. I should have been drawing like a little hangman out there, but I forgot this time. It is our visible light. That's the line spectrum that we saw for hydrogen. Hydrogen is jumping according to those equivalent energies. And when it comes back down, it is releasing that colored light. The purple one, was that a really big cattle prod jump or a small one?
Small. Or big.
That was a big one because violet was higher in energy. So we're looking at a very large jump back down. The red one would be a very, very small one. So if we were forced, okay, and this is arbitrary, so please don't assume this. There's our electron way back at the top. What color would we expect for going from that first one to the next one down? Why do you say red for that? That's a small energy gap between them. So we'd be picking the lowest energy light that we could. The specifics of what color light that is irrelevant. We're either picking red or blue, pretty much, or red or purple. Okay. What about if we jumped from red, or sorry, not red, from that top dot all the way down to here? Okay, that's now going to be our higher energy. That could potentially be our violet.
Takes more energy to go.
Because it's not that it takes more energy to go down, it's that is a larger drop in energy. Remember, the further out we get, the higher in energy it becomes because the further it gets from the nucleus, the more charged it becomes. Okay? Was that all the possible transitions I could do to get back to my ground state?
Hang on, you just said the further out we get, the higher energy, but
The
isn't
higher energy.
the closer we get to the nucleus, the higher energy? Instead of,
Closer we get to the nucleus, what happens?
oh, it's neutralized.
It's neutralized, it's lower in energy. Okay. Did we look at all our possible transitions here? What transition did we miss? Someone said no, and someone started to say yes. Orbit 2 all the way down. What color would we expect there? Somewhere in between our blue-green, and that's all I got, is this really dark green. Okay. The exact color is not important. It's just recognizing the pattern, okay, on what we've got. Kind of makes sense? Okay. So this is kind of Bohr's theory, that we have quantized energy levels. We have steps. Okay. That's the point of looking at the staircase. That's the point of looking at the ramp. We don't have a continuous spectrum. We have quantized energy levels. So we have individual steps that move down. Okay? So that's the beginning. Questions on that? Okay. You might regret that. So this is the evidence we have for our energy levels. We're looking at transitions between those. Notice that we've now scaled this up significantly more from what we had before. So that first one that I've got in a purple arrow, why would I draw that one the largest, or sorry, purple?
This is violet.
It's a really large jump. Large jump means more energy, which means more purple. Not darker, more purple. Okay. How about the next one?
Less of a jump.
It's less of a jump, so it should be lower in energy. So we're moving from purple, moving towards red. I didn't show red because red, being the last one, is the shortest jump here. Okay. Notice the extra information here. We're saying for red, we're going from what level? 3 to 2.
1, no.
That's interesting. It's 2. 1 is further in. How about the blue? We're going from 4 to 2. Purple? 5 to 2. Why are we not going to 1?
It's only 2.
Who said that? It's not visible. Okay. The gap to go from, say, 2 to 1, that energy difference is enough that we can't see it. Okay. So only certain transitions are in the electromagnetic spectrum that we can see. Other ones aren't visible. It's as simple as that. They are still possible, we just can't see them. Kind of make sense? Okay. Oh, shoot, should have deleted that side, ignore that. So if you guys see them, completely ignore that, right? If you printed it out, big line. It says RWS and randoms. That would all be stuff from last semester that I forgot to delete out. So you don't need to worry about it.
You have this stuff to print out before class?
Are the slides available on Canvas? Yes. It happens. Which brings us, well, not quite the nice segue, but we end up with our atomic fingerprints. Okay. If we looked at hydrogen, we had 3 lines. Helium, how many lines do we have? 1, 2, 3, 4, 5, 6, 7, 8. Lithium, 1, 2, 3, 4. Notice that we get different lines. Why would we get different lines? I mean, it's still just an electron jumping. If I move from hydrogen to helium, all I'm doing is adding an extra electron and an extra proton, but wouldn't I still be expected to have the electron jump from 3 to 2, 4 to 2, and 5 to 2?
It's the different principles.
Close, but not quite.
Do orbitals have different distances between them?
Why would the orbitals change as we change the element? There's more electrons. As we add more electrons, what happens? The electrons start to fight with each other and change their energy. Is it a lot? No. Is it enough to cause a different atomic line spectrum? Yes. What else changes? Kind of, sort of. What do you mean by size of the nuclei? We have more protons. If we have more protons, we're now going to attract the electrons tighter. Is that going to change the energy level of my electrons? Yep. If the electrons change their energy, what happens? Line spectrum changes. Okay? And it changes significantly and characteristically enough that we can identify them according to their fingerprint. We can take an atomic line spectrum and we can say that if I see that, that's helium. Okay? I could blend all of these together, and if we were good enough at separating and finding patterns, we would be able to separate those out and say that actually that combination is helium, lithium, sodium, and mercury, by looking at exactly how those lines separate out and total out to give us those individual elements. Do scientists do that? Yes. They're called astronomers. Okay? Or, what's the other one? Astrophysicists. Okay? They're looking at telescopes aimed out at distant planets and suns, and what are they trying to detect? They can look for atomic line spectra to determine the concentrations of, say, helium, lithium, sodium, or mercury. And those concentrations they can tie back to the lifetime of that sun, all by looking at the atomic line spectrum. That's pretty freaking fascinatingly cool. Okay? So for that, you should talk to Angel Fuentes, because he's our local astronomer. So he offers lots of classes, so you can take classes with him. Okay? Or you can take a physics class. Sean's a good guy, but I don't know that they talk about atomic line spectrum. That astrophysics gets kind of out there. Okay? That's why you got to go to Angel. Okay? So we can use this as a fingerprint. Is this how we would always identify compounds? Why not?
Is there simpler ways to do it?
There's easier ways to do it. We all have fingerprints. Okay? You didn't wait to scan my fingerprint at the beginning of class to be like, is that actually Mike? Okay? Is he supposed to be teaching me, or is he just an imposter? Okay? We have other ways of doing it. To get those line spectrum, what do we have to do to the element?
Excited.
Excite it. What phase is the element in to get excited? Gas. Are all of our elements gases? No. To get them up to gases, might that be difficult for some of those elements? Yeah. We're going to have to put in a significant amount of energy to get them up into the gas phase so that we could hit them with a cattle prod. Okay? So while it is useful, it is something that is typically reserved for astronomers and astrophysicists, because where can we find that much energy? Suns. Okay? The simple ones we use to help us identify and look at or come up with electron configuration, electron orbitals. Okay? And we also use to light up bars. Okay? Your neon lights. The color of your neon light is due to? It's actually not neon. I think it's krypton. But it's one of the halogens being excited with a cattle prod. Okay? And we've trapped that in a tube that then glows for us. Okay? That's kind of neat. That's what we're using them for. So let's actually take this to the next level. Okay? So what Bohr was doing with his model was said we had distinct homes for the electrons, or distinct steps. Okay? And we have a couple extremes to look at. Okay? Unfortunately, because of how I got this drawn, the nucleus is kind of down at the bottom, and those watching at home can't see this. The nucleus is actually not here. The nucleus is probably down here. Okay? Maybe even down in the geology room down below. Really far away from that first energy level. Big, big, big distance. Okay? What happens as I move further from the nucleus? More energy. Keep moving further from the nucleus. What happens?
More energy.
More energy. Okay, let's start to quantify it. Okay, if we were really close to the nucleus, would we say that electron was part of the atom? Yeah, it's associated with it, right? What happens if we move further away? Still part of the atom. Further away. Further away. Further away. Eventually what happens? The electron is now so far away that is it affiliated with the nucleus? No. What it's done is it's reached vacuum. It's no longer associated with anything. Okay? So we have an upper limit. That upper limit is defined as our vacuum. Okay? That's all the way up here. How do you spell vacuum? Here.
Yeah.
I don't know where I got it. Vacuum. Okay? Don't give me a hard time for that. That's not that bad. There's worse words. Okay? So if we start here, where's our next energy level going to be? Let's avoid color for the moment. Down here? Where's it going to be? Above it. How much further above it? It's going to have to go above it, for sure, because we're starting to get further and further away. Okay? So let's say it goes maybe here. Where's the next energy level? Okay? So that same distance, right? Next energy level? What do you mean in between? I like where you're going with that. Halfway between what?
That energy level in the vacuum.
And the vacuum. Remember, those energy gaps cannot be the same. Okay? Because we have an upper limit. Okay? Eventually I hit the vacuum and I'm gone. So what actually ends up happening is something more along these lines. Okay? Our orbitals will get progressively further away, but progressively less far away. Okay? And they end up getting closer and closer to each other until eventually we reach the vacuum. Okay? What would that suggest about the size of an atom? Is the size of an atom finite? Is it defined? Can we get larger and larger atoms to infinity? Probably not, because what happens? Eventually, we hit the vacuum. And once we're in the vacuum, it's no longer part of the atom. Okay? So we have kind of this finite level. How many energy levels have we discovered? Okay, and remember, that top one was the vacuum. How many do we have? How do you know there's 7?
Count the lines.
Because you saw me counting them. I could have been lying. How do we know there's 7?
Well, first, you're saying that the first level is actually not seen, so you have to still count that as your first level, energy level, right? And then the other one.
No. So what we were looking at with that first energy level just wasn't visible on the slide. There was still a first energy level, and we could do a jump there, but that was not visible light. The orbital still existed. Okay. We have 7 distinct lines here. So that would suggest 7 different energy levels. I wonder if there's a place where we compile all of this useful information that we could then quickly access. Like on the walls.
I don't know, the periodic table?
Oh, periodic table. Where do we see 7 on the periodic table? Nitrogen sure has 7, yeah. That doesn't make sense with energy levels. That's an atom.
Isn't there like something?
1.
The rows.
The rows in our periodic table happen to number 2, 7. You might say, well, doesn't this make it 8, 9?
No.
Why is that not 8, 9? Those are inserted into the periodic table. Okay? Those go in where it says 57 to 71, 89 to 103 on our periodic table. Why do we pull them out? Okay? Because we're scientists. We love squares. That wasn't that bad. Come on. That was pretty good. Okay? If we put in those elements into the middle, what happens to our periodic table? It becomes really, really long and not very square. So what do? We pull those out just a little bit so that it becomes a little bit more square. Okay? That's why they're pulled out. Second reason why they're pulled out. How often do we work with them? Almost never. So we might as well pull them out so we can just kind of ignore them. That's kind of what's happening.
Aren't those the radioactive ones?
Some of them are radioactive, yes. Most of them are radioactive, yes. Okay. If not all, actually. Okay. So our periodic table tells us the energy levels. We got 7. 7 rows. Cool. Let's name those energy levels. Let's name the first one. Come on, creative people. What do you got? Red, not a bad guess. I can accept that one. But I don't think we really want to memorize red. S is actually not an energy level. Come on. What do you want to name the first energy level?
1.
Oh,
How about the second energy level?
started at the top. Never mind.
Trace.
I didn't say we were creative. Okay, there are energy levels. They're numbers. 1, 2, 3, 4, 5, 6, 7. Cool. Okay. These represent where we can place our electrons. Okay. So what happens if, let's just do it. Let's put an electron in. Where would I put the first electron? In the 1, because?
Has to be next to it.
Why do I want it next to the nucleus?
See how it's going to react?
So you can start it?
No, what did you say?
Because it neutral, that's where it's neutral. and
It's
it
most neutralized, which means it is lowest in energy. We always want to fill lowest energy first. So we start there. Next electron goes where?
Still 1.
Still 1. What's the charge on an electron? What's the charge on another electron? What happens when I get 2 negatives near each other? They repel. You still want to put a second electron in that same level? Okay. So I don't like that theory. That doesn't make sense. We shouldn't put an electron next to an electron. It needs to go into a new energy level. How many elements can I make? Not very many. We can do a little bit better than that. We'll get to not very many later. 7, because there's 7 energy levels. Does that explain the periodic table? No. What does that mean? My assumption of not being able to put 2 in was wrong. Okay, so maybe you were right. Turns out that yes, we can put 2 electrons into any given orbital. Okay? And yes, that is careful word choice. Okay? How do we avoid that negative-negative repulsion?
Opposite sides.
This is really kind of silly, but this is how we do it. Versus what'd you see? The direction of the spin. Electrons have a spin associated with them. That spin, as long as they're in opposite spin states, they don't communicate with each other, so they can be neighbors. So I can draw that in. Cool, so that means every energy level I can put in 2 electrons. So how many elements do I have? 14. Good, we like the numbers, not just small. 14 elements, cool. That is more than 7. I'm now doing a great job. 118. So what does that mean? I'm missing something. So there's an interesting idea. The higher I get, the more I could fit. Why is there more room? Why is it wider? I agree with that. And sublevels and all that are correct, but let's get more into the physics, or not physics, geometry of this. Say that again. Lowest energy level, right? There's our nucleus. There's our first energy level. Where's the second energy level? Which has more area? The second energy level. If I have more area, what can I potentially do? More electrons. Okay? That more electrons actually gets quantified. Okay? It turns out that as we jump up in energy, we end up adding types of orbitals. So at the first energy, I only have one type of orbital. That's all I got. But as soon as I move to the second energy, I can now have a different type of orbital. A new type. So that second energy level splits into 2 things. They are very close in energy, but they're not the same. Okay? What happens when I move to the third energy level?
3 sublevels.
I will get 3. The fourth?
4.
I don't have a yellow. 5?
5.
6? 7? Okay. So you get the idea. Now, how many atoms can I explain? A lot more. Does it explain all of them? No. Something else is going on here. It turns out that when we scale upwards, yes, we get a new orbital type. Okay? But because it's a new orbital type, it also gets a new
Set of sublevels. Or at least
close
one sublevel.
Okay? How do you know my pencil thingy? No, I'm not saying that. My iPad pen is different than the whiteboard pen.
Because the iPad pen doesn't actually write, unless it's on an iPad.
I would beg to differ because there's actually a rubber there that will definitely mark the boards.
Unless it's okay.
They look different.
What's that?
They look different.
How do you know it looks different? What would you say is different about that look? I'm totally fishing for a one word. S is a good word, but I don't like the Z's. Shape. The shape changed. Guess what happens when we move up? Not only do we get a new orbital, we get a new orbital shape. Why is that then relevant to us? Okay, well let's look at what's happening with these. What is the shape of the first orbital at the first energy level?
Well, circles, but the next page is put off.
Okay. So we're here to circle, and we're going to challenge that statement. Yes, that looks like a circle. What is it representing? A sphere. We're three-dimensional. It's a sphere. Okay? When we move up to the second energy level, what is going to be the lowest energy orbital shape? Still a sphere. We will repeat whatever we had. Okay, so the lowest energy one is a sphere. I'm not liking that blue on that screen, so let's try that blue. Let's see. Does that show up a little better?
Yeah.
So there's our sphere. What does the next one look like?
No, it's because you're adding more electrons, so I think they're going to be forward at a different end. So
No, we don't even do that. What's it just next one look like? A what? Or people just, I'm hearing people shout words, but none of the words are making sense to me. No, it won't be the same thing. So here's why. Because remember, we said when we move up to a new orbital type, what has to happen? Different shape. So it can't be a sphere, because it has to be a different shape. Oval's not a bad guess, but no. You all read the chapter, right? There we go. There's the word we're fishing for. We get the dumbbell shape. Okay? You know, kind of like lifting weights. Like it's like right there, little dude here, little arm. He's kind of curling it. I just haven't drawn the rest of his body. Calm down. Jeez. Is he a little dumbbell? Yeah.
Draw biceps.
He's working on the wrist at the same time. So we have that different shape. Let's ignore the man. Okay. What is now interesting about these shapes? So we said I only have one that looks like a sphere. But then when I move up to the dumbbell, now something weird happens and I get multiple dumbbells, or multiple of those. Why would I get multiple of those? Take that sphere, right? You've got a sphere. I'm holding a sphere. Okay, if we all closed our eyes, and you open them, did I spin the ball?
I don't know.
Why do you not know? The sphere is perfectly symmetrical all the way around. There is only one orientation for the sphere, which means how many orbitals? One. What happens with a dumbbell? Would you be able to tell that I rotated the dumbbell?
Yeah.
Yes. It turns out that through the quantum mechanics and physics of it, that we end up with 3 distinct orientations for the dumbbell. This is always the fun one to draw here. Okay. We get one on the y-axis, one on the x-axis, and then one on the z-axis. You get 3 orientations. 3 orientations means 3 orbitals. Yes. Which then means what happens as we start to fill electrons. So our first electron will go where? In the bottom. I like that. Be more specific.
In the bottom spectrum.
More specific.
First orbital.
First what?
Orbital. First sphere.
I'll accept, we didn't talk about the name, so I'll accept first sphere. I'll accept that. First sphere. Where's the second electron go?
Second sphere.
First sphere is like opposite.
First sphere, opposite spin. Okay? So that's our explanation that we've got right now. Third electron. Second sphere? Yes. Fourth electron.
Second sphere.
Opposite spin. Where are we? 5? 5. Second dumbbell. And I didn't draw any lines. So instead of drawing those shapes, I could draw lines just to represent those. So it goes in there. Where's the 6th? Okay. I've heard a suggestion to go into the second dumbbell, same one. Everybody agree? Or you want to challenge? Throw the red flag. That was a football joke. Come on, red flag. Challenge that. What's the challenge? Where else could it go? The next one. We either put our 1, 2, 3, 4, 5, 6th electron into our red arrow or our purple arrow. Where should we place it? We're placing it in the red one. What are you saying you're doing? Oh, interesting. Lowest energy level. How do we know the 1s was lower, or the 1 sphere was lower than our 2 sphere?
Because it's closer.
Drawing. It's easier. Why is the 1 sphere lower in energy than the 2 sphere? It's the bottom of the page. Right? You said you want to put an electron into that red section there because it is lower in energy than the line right next to it.
Technically, with sublevels, right? No?
No. Technically, it's the opposite, actually. Those are at the exact same energy level. The only reason we placed an electron in a pairing was because there was no other energy to go to. We're picking our lowest energy option. Do I have a lower energy option?
Yes.
Where's lower in energy than those? No. So now the question becomes, where should I put that next electron? It's not a lower energy option, but what happens if I pair it? What do we say happens when electrons get near each other? They go higher in energy. So if I put an electron in that red arrow, what happens? I go higher in energy. What if I placed it in the purple one? Stays the same energy. How does it fill? Purple. Where's the next electron go? And the next one over. Next electron.
Now you can put it on the first line of the second.
Now we'll go back to that first line. Why did I not jump up to say the 3s? 3 sphere, 3 sphere. The 3 sphere is higher in energy than my 2 dumbbell. So I will fill all of the 2 dumbbell before I move up to that next energy level. Kind of shaky? Kind of there? Okay. So it's just a question of that fill pattern, where we place those electrons. Okay. We will always start lowest energy and then slowly work our way up. If we're given the option of 2 equal energy places, we will always place the electron in the unoccupied orbital. Don't pair electrons unless you have to. You have to because there's no other lower energy option.
So those 3 lines you drew up on the board here, those represent the orbitals
Those represent the different orbital orientations.
for the 3rd level, right?
Nope. For the 2nd energy level, hence the blue, but a different shape. So we start at our energy level, 1, 2, 3, 4. I tried to color code those, and I actually did that. Okay. But then as we move up in energy level, we get a new shape as an option. Each of those new shapes has an issue with it. When we change the orientation, we can see a difference, which means we get multiple of those. Okay. You really want the big monkey wrench? Too bad, you can get it anyway. 3rd energy level. We go up to 3rd, and we'd have the lowest one being the 3rd sphere. Then it would be 3rd dumbbell. How many orbitals would there be at that dumbbell level? 3. Same deal, orientation.
And then you follow each one up twice.
What's the next one? So 3rd dumbbell, and then what I'm asking for is right there. What is that shape?
Looks like a tie, maybe, like a windmill thing.
You have weird ties. Okay.
Double dumbbell.
Nobody goes after me, Lucky Charms.
Okay.
What is it?
Clover.
Cloverleaf. See, you got it. That's all that matters. There we go. We've got a cloverleaf. So we got sphere, dumbbell, cloverleaf. Okay? Issue with sphere, dumbbell, and cloverleaf, they all involve too many letters. Okay? And I can't spell, clearly. It tends vac. Okay? So I want to come up with a better name than sphere for the circular one, for the spherical one. What do I want to call it? I will call it an S. How about the 2nd energy level one? Yes. It's not just S. That second energy level one is 2S. I need to differentiate it from the first one, which isn't really just S, it's the first dumbbell. 2P, as in Pumbell. Anybody speak German? No Germans? Dumbbell in German begins with P.
That's the weirdest thing.
Interestingly enough. Just don't Google that. That is not true. What is the lowest third energy level orbital?
That one, D, isn't it? Oh, D? 3S.
3S. You're jumping. Next one up.
3P.
3P. Next one up. Ah!
3P.
Gave away the answer. Next one up is the 3D, because in Italian, cloverleaf begins with D.
Is that
No.
right back there?
Okay. Why do we use those symbols? Blame the physicists. That's what they came up with. I think it was the physicists. Okay. So that's an awful lot of information to remember. So the S, we could fit in only a total of 2 electrons. The P, how many electrons could we fit in all of the P? 6. How many could I fit in a single P orbital? 2. But because there's 3 P orbitals within the P type, I can fit 6. Okay. D. The question would be, how many can I fit in the D? In a single D, maybe that's where you're going. Single D orbital fits how many electrons? 2. It's the same amount. Every orbital holds 2 electrons, period. But in the type of D orbitals, how many electrons can I fit? Ooh, lots of numbers. Okay, so let's see here. Okay. Periodic table, we had our energy levels, right? Our energy levels represented which on our periodic table? The rows, also known as the periods. Okay. So that's our energy level. What would we hope is also somehow buried in our periodic table? Maybe something about the orbital type. Okay. So let's start. Hydrogen, it's the very first electron. So if I'm just going to write this out now, hydrogen has 1 electron. Where does that 1 electron go? The first energy level, so 1, which type of orbital? S. There's only one option. How many electrons are in that? 1. Because it's hydrogen, it can only have 1. So I need to specify that 1 in there. Okay, we haven't talked about this yet, but where do we specify information about the amount of electrons? The upper right-hand corner. The upper right-hand corner is always where we will find information about our electrons. It can be buried and hidden, but that's where we'll find it. When we're looking at this electron configuration, I put 1 there to represent 1 electron from hydrogen. Good. Okay. Let's now move to helium. What is helium's electron configuration? Where's the first electron go? 1s. 1, right? There's 1 electron. Where's the next electron go?
Same place.
1s1. That gets a bit redundant, so what could we do? 1s2.
Why would we write it as 1S1?
What's that?
Why would we write it as 1S1 if it was, or to the power of 1 if it was helium?
We didn't say it was 1s1. We said it was 1s1 for the first electron,
Right.
and then we said it was 1s1 for the next electron, because we're only specifying 1. The combination of those is 1s2. We're going to move there, yeah. But we're going to go slowly. Next step. Lithium. Electron configuration. 1s1, next electron. 1s1, next electron. 2s1. Again, redundancy. We good? Beryllium. come to you in just a second. 1s2, 2s2. I'm going to have to get rid of that helium. Boron. 2 what? 2p1. Hydrogen, what was its electron configuration? S1. Lithium, electron configuration. S1. Interesting. What do you think about sodium? It's going to be S1. We will still have all the other previous energy levels filled underneath it. Okay, so sodium will be 1s2, 2s2, 2b6, ignore that, 3s1. Beryllium, 1s2, 2s2. Hydrogen and lithium were in what column? First column. Beryllium's in the second column. Interesting. In the first column, I had S, the 1 electron in it. First one, cool. Beryllium, in the second column, and it becomes 2. What might we expect? I'm going to incorrectly stand in front of one screen. Don't look at the other screen. What do we expect for our boron? It's in the third column, right? So wouldn't we say, when we say 1s or 2s3? Oh, but it didn't say 2s3. What did we say? 2p1. Is boron immediately next to beryllium? No, there's a giant gap there. Guess what those first 2 columns are typically referred to as? As a hint, it begins with S and rhymes with lock. It's really bad. It's sorry. It's referred to as the S block. Because, yeah, you guys are processing the rhyming now, yeah. The S block, because if we look at the outermost electrons for any element in those first 2 columns, the outermost electrons are in what type of orbital? S. How many electrons can fit in an S orbital? 2. How many columns are there? 2. 1 for the first electron in the S, 1 for the second electron in the S. We now have this massive gap between beryllium and boron. In that massive gap, what are we transitioning to? The P block. The first column being the first electron that goes into the P block. Carbon, 2p2. Nitrogen, 2p3. Fluorine. Figured that was going to cause a pause. 2p5. Neon, 2p6. How many electrons could I fit in the p orbitals? My arm's going numb. 6. Why? Our electron configurations just predicted it. Our column just gave it to us. What happens after neon? We now move from neon to sodium. Sodium was part of which block? The S block. Which means if we were going to look at its outermost electrons, it's going to fill S1. Which energy level? Why did you say 3? It's in the third row. You ever played Battleship? Guess what your periodic table gives you? The coordinate system for your electron configuration in the form of Battleship. Pretty awesome. Okay? So it is all set up on there. You don't have to really memorize all of these pictures and fancy stuff. That's ultimately where it's coming from. That information is stashed already on the periodic table. Sweet. You're given answers. The problem with those answers, you have to be able to interpret them. And that interpretation requires practice. Okay? Back to the question I asked. D. Said how many orbitals for D? We'll take a step back, make it an easier question than that. How many electrons could I fit into D?
Wasn't it like 10 or something?
How many electrons could I fit into the S? 2. Where was the S block? The first what? 2 columns. 2 electrons, S block. Ooh, interesting. P block. How many electrons can fit in the P orbitals? 6. 3 orientations. 2 orbitals, 2 electrons per. In our P block, how many columns? 6. Do we see another block potentially in there? We block out the S, block out the P, the transition metals, also known as the D block. How many electrons would you expect to fit in the D orbitals? 10, because how many columns are in the transition elements of the D block? 10. How many orbital orientations are there for the D block? How many orientations are there for the D orbitals? A lot of different numbers. How many orientations were there for the P orbitals? 3. Each orbital could hold how many electrons? 2. How many columns do we have in the P block? Columns in the P. 6. Divided by 2 gets us 3. How many columns in the D block? 10. Divided by 2 electrons per orbital gets me 5 orientations. Do we have more than the D block? Yes. There's another one. Where do we have information about that other one? That whole section that we pulled out? How many orientations do you expect for that new orbital type? Orientations, I tricked you. 7 orientations, because how many columns are in that bottom section? 14 columns. Each orbital can hold 2 electrons. We have 7 orbitals.
Where can I read that?
Okay? So when we look at all of this, you might panic and say, okay, this is kind of crazy, this is a bit nuts. This is where electrons live. And there's no way I would ever remember this because we never do anything like this before. Where do you live? Do you live in a state? Is that all the information you give people? I live in Arizona. Oh yeah, I totally know how to find you. Okay. Do we have, say, maybe a city? Or maybe the street? Or the address? Each of those statements that we use every day to give to people to say how to get to our house as an address are the electron homes. Those are the orbitals. Those are where the electrons exist. It's the exact same process. I'm not saying that makes it easy, okay? Because God knows I don't want to try and find your house, because that's probably going to be a pain, okay? But that's the same process.
So when we write the electron address, that's like if you wanted to find my house, starting on your street, knocking on every door, saying, hey, does Jerry live here, right?
For the full electron configuration, yeah, absolutely, you're right.
Oh, it's terrible.
Yeah.
So I was reading about that, and each orbital has the same amount of sublevels for that orbital. Like 3 has 3, 4 has 4, right?
Yes.
10 has 10, and so
Yes.
on. How many energy levels are there?
We answered that already. How many energy levels do we have? 7.
Well, no, it was saying that
Could we theoretically go up to 8? Yes. Why are we not there? Because we haven't made a nucleus big enough to do it, number 1. Okay. Number 2, what was the other issue? We eventually reach the vacuum. Once we're at the vacuum, we can't get any bigger. The electron's not affiliated with the atom anymore. It disappears.
something about 10 energy.
We could theoretically continue to go. That doesn't mean we're there. Yeah. You should actually be happy with that theory because we don't have them in reality. Okay. So our orbital types, we have 3 primary orbital types. Those pictures and images that we work with are actually probability shapes, which nobody likes understanding, so don't stress too much about it. They're just the way to describe where the electron is 95% of the time. So when I look at the 1s, or in this case because it's labeled 3s, when I look at the 3s orbital type, I'm at the third energy level, and I am s, so it's a sphere. 95% of the time, if I have an electron in that 3s orbital, I will find it within that shape. If I move to arbitrarily the 2p orbital, okay, 95% of the time I find it within that shape. If I move to the d orbital, there's our cloverleaf shape. Okay? And what we're looking at is the different orientations to get the different types or the different numbers of those orbitals. The sphere has how many different orientations? It only has one orientation, so there's only one s orbital. The p orbital has multiple orientations, and yes, you get all nuancy and flippy weird angles and all that. Be simple, x, y, z. Those are your primary axes. That's going to be your orientations for the p orbital. Okay.
My question real quick was, where's the nucleus in these?
The nucleus is dead center in the middle of each of these. Okay. The d orbitals have the cloverleaf shape. Again, those don't look pretty. They're kind of off of weird axes. Okay. If we break them all down, we get our p orbitals. You ready for the d orbitals? There's our cloverleaf shape. And now we just change the orientation. And we get all 5 orientations all making sense. Except maybe that last one. That last one doesn't look like a cloverleaf. That more looks like a dumbbell that's been eating a donut. Okay? And that's pretty darn close to what we call that one. Okay? Those are the orientations and the shapes that we see. What we're responsible for knowing is how do we then fill and use these. Okay? So if we look at the first energy level, what are the sublevels? Well, there's only one. It's the s. How many electrons can I fit in an s orbital? 2. Which would then mean I could write a magic 2 here. If I want to now look at the total electrons in the energy level, so that is summing all of the orbitals that begin with 1. Not s. 1 is the energy level. S is the type of orbital. How many electrons do I get? 2. Oh, that was a bit silly. What happens if we make it the second energy level? How many different types of orbitals do we have? 2, known as the 2s and the 2p. How many electrons can I fit in the s orbital? How many electrons can I fit in the p-type orbitals? How many electrons are in the energy level? Make sense? If we moved up to the third energy level, come on, whoa, there you go. Third energy level, we end up getting in 18 because we get 2 from the S, 6 from the P, and 10 from the D. That's where those numbers are coming from. They're corresponding to the energy level, not necessarily the orbital type. And with that, I will end, and we will pick up there.